Chapter 5 is a fun chapter because we get to show that general relativity and quantum field theory are indeed compatible. So the whole search for quantum gravity started, well, I guess it started prior to the vacuum catastrophe. People were trying to unify, the strong and nuclear forces and other quantum mechanical effects with general relativity ever since the beginning. But sometime in the 60s and 70s, I think is when it was, physicists started finding incompatibilities with cosmology and quantum mechanics. And one of the reasons that this problem came about, there were several problems, but one of the main issues, I guess, is the vacuum energy density. And this is the idea that all quantum fields have a lowest energy state, what they call a ground state. And this energy per unit volume is called vacuum energy density. When you use observational data and quantum mechanics to calculate the energy density, you have to do it across multiple or all possible modes. And they are only using a maximum cutoff scale, which they think is like the Planck scale. And so it goes to infinity because they have no minimum scale of which to cut off. So you end up with this extraordinarily high value. It's like 10 to the 20 or 10 to the 120 orders of magnitude too high. It's like 10 to the 113 joule meters cubed or something like that is the energy density that's predicted. But we can actually observe, like through Hubble's law, if you're using the paradigm lambda CDM, then you can kind of just measure the energy density, and it's a lot lower than that. It's 120 orders of magnitude lower. So in chapter 5, I'm able to revisit this problem because I have 3 new things in my toolkit. I have scale dependence. This is an absolute necessity. And, there's been quantum physicists talk about scale dependence and energy density in the past. But I also have 2 natural cutoffs. The emission point of the Hawking radiation from the horizon and the horizon itself. So that gives us a smallest possible scale around 2 Planck lengths and the largest possible scale around 13 billion light years. This gives us a lowest vacuum energy density that's calculatable. And so we can just skip the entire regularization procedure, and that makes general relativity compatible with quantum field theory. I don't know. That's quantum gravity. But, it's not quantum gravity because it's just general relativity. To me, it's remarkable. I love it. I don't care what anybody else thinks. I really do care. I do care because I think this is right. And, it's, I'm passionate about it. But it's like these physicists, man, you could lay a chunk of gold in front of a physicist and he'd be like, it's not perfectly spherical. I don't want it. I did the best I can, man. I've got 0 good feedback, but to me, this makes total friggin' sense. This makes way more sense than any other published material out there as far as quantum gravity goes. So, take it with a grain of salt, but this is it. This is it. Anyways, there's something else I want to mention that I don't remember reading this in my book, and I don't remember doing commentary on it, and it may pop up in future chapters. But this is it's a bigger part of my theory. I don't even have a theory. This is not theory. This is just corrections. I'm just correcting physics. I'm saying, no, you have to do this, is all. Like, it's just, like, they didn't dot their I's, in my opinion. Like, physics was almost done. Like, it was seriously, it's just like all they did wrong was believe that the universe was expanding. That was the only mistake. That was basically, essentially the biggest mistake that caused a domino effect. But there's something else I want to talk about. And that's this idea of, the holographic principle. So the string theory has its foundations in something called the holographic principle. And the holographic principle is this idea that there's a strict, way more strict, definition than I can give it here. So I'll just pause and look it up. But the idea is just that you can have, I'm looking it up right now, that you can have all of the information on a 2D surface. So, okay, this is from ChatGPT. The holographic principle is the idea that all the physical information in a region of space can be fully described by the degrees of freedom living on the boundary of that region, like a 3D volume being encoded on a 2D surface. And so the idea is that you don't have to look inside of something to know what's inside of it. All of the information is contained on its surface. Now you have to be able to decipher it and all of that. That says nothing about how you can decode the 2D encoding, but that's the general idea. The motivation is black holes and entropy. And so one consequence of this is that the number of physical states or configurations inside of a volume, it's bounded by the boundaries area, the surface area, not by the volume itself. This had me just reading this definition one day, just encountering it, and I briefly looked it up. I think I was studying fractal cosmology. Anyways, I briefly encountered this one day, and then I just happened to do the calculation. My profile, this 1 over R profile, I keep saying it's 1 over R, but it's proportional to 1 over R. So the mass density for a given volume is proportional to 1 divided by its radius. Now, it's actually not exactly 1 divided by the radius. It's this coupling constant K that I've been saying, and it's 0.833 kilograms per meter squared times 3 divided by 2R. And so instead of 1R, it's K3 or 3K divided by 2R. That's the density for the given volume. If you want to find the density for a given volume in the universe, for any given volume, now this is for cosmological scales, really, because obviously if you're looking at a star, it's going to be close. This is close. Like, it's close to galaxies and stars. But, it gets better on larger scales. Scales beyond one megaparsec, say. But regardless, this K, this coupling constant K, I got that from Hubble's law. But the surface area of the observable universe that it creates, so because we are using gravitational redshift instead of Hubble's law, but we have a universe that is still bounded by the observable limit. So you can't see beyond the observable radius. So it's kind of like you're inside of a spherical object. The boundary of it, the horizon, has a surface density of 0.833 kilograms per meter squared. So this mirrors the holographic principle. It said there's something there. Our horizon contains is the coupling constant. I think it's actually 2 times the coupling constant, or it's divided by 2. I should have looked this up real quick. I just thought about it because I got to the end of the chapter and there was nothing about the surface density. But in short, the surface density of our observable universe is what creates this 1 over R proportionality, or the density distribution of 3K divided by 2R. That's it. And so it's the holographic principle is true because this is for the observable universe. Anyways, that's another interesting tidbit I wanted to add. So next up, chapter 6.